Electrolysis is using an electrical current to bring about a chemical reaction. Not all substances are affected by passing an electrical current through them, only compounds with ionic bonding. The effect is always to break down the ionic compound to produce elements. We use conducting rods called electrodes to pass the electric current through the ionic substance, and it is important that we make these from materials that will not themselves react, such as graphite or platinum. The proper name for the ionic compound we're going to break down is the electrolyte. To be an electrolyte, the ions in the ionic substance must be free to move, not locked up in a giant ionic lattice, so we have to either melt the ionic substance or dissolve it in water before we can get an electrical current to pass through it. We can test to see whether a substance will act as an electrolyte by seeing whether we can pass electricity through it. The electrodes also have special names. The positive electrode is the anode. Because opposite charges attract, the negative ions in the electrolyte, which we could also call anions, will be attracted to the anode. The negative electrode is called the cathode. Positive ions, which are called cations, will be attracted to the cathode. Here's how it works. To start with, the electrolyte contains positive and negative ions, free to move around. When we connect the power supply to the electrodes, the negative ions are attracted to the positive electrode, and the positive ions are attracted to the negative electrode. The negative ions give up the extra electrons from their outer shells to become ordinary atoms rather than ions, and these electrons travel from the electrode to the power supply. Electrons then travel to the negative electrode and into the outer shells of the positive ions, making them uncharged atoms too. So at each electrode we're turning ions into elements. Two more terms we need to know are oxidation and reduction. Oxidation is losing electrons, so the negative ions get oxidized when they lose their electrons at the anode. Gain of electrons is called reduction. The positive ions at the cathode are getting reduced. We can use oil rig to help us remember this. Oxidation is loss and reduction is gain of electrons. So electrolysis is an example of a redox reaction. Some examples will help us understand exactly how this works. The simplest case is electrolysis of an ionic substance which has been heated until it melts. We'll use copper 2 chloride as our example. So we heat the copper chloride crystals until the lattice melts and the ions are able to move freely. Then we connect the power supply and the ions move towards the oppositely charged electrode. From the name we know that the electrolyte contains copper ions with a 2+ charge, hence copper 2, and we should know that chloride ions have a 1- charge because they have a valency of 1 and they are non-metals. A different reaction happens at each electrode. There are really two reactions going on at the same time. The copper 2+ ions are being attracted to the negative electrode. The electrode gives 2 electrons to each copper 2+ ion, turning each into a copper atom. In this way, a layer of copper metal begins to grow on the surface of the cathode. The element copper is being formed. We can show what is happening by writing an equation. Each Cu2+ ion gains 2 electrons to become a copper atom. We call this a half equation because the other half of the story is what's going on at the other electrode. The positive electrode has attracted the negatively charged chloride ions. Each chloride ion gives up 1 electron to become an uncharged chlorine atom. The chlorine atoms bond in pairs to form molecules of the element chlorine, so we see bubbles of pale green chlorine gas forming at the anode. We can use a half equation to show this too. 2 chloride ions turn into a chlorine molecule by giving up 2 electrons. If we combine the two half equations, which we can do by adding them together, we can see that the overall effect of the electrolysis is to turn the ionic compound copper chloride into the elements copper and chlorine. Now we'll take a look at electrolysis of ionic compounds which have been dissolved in water. The difference, compared to melting an ionic compound, is that there are two extra ions present in the solution. These are H+ or hydrogen ions and OH- or hydroxide ions. These come from water molecules which have split up into ions. This means that in a solution of sodium chloride we will have two kinds of positive ions, the sodium ions and the hydrogen ions, and two kinds of negative ions, the chloride ions and the hydroxide ions. Both types of positive ion will be attracted to the cathode, and both types of negative ion will be attracted to the anode. There is a rule that we can apply to work out which of these two types of positive ions gets reduced at the cathode to form an element and which one is unaffected. The rule is that if the metal ion is less reactive than hydrogen, it gets reduced and forms a layer of the metal on the cathode surface. If the metal ion is more reactive than hydrogen, it stays in the solution and the hydrogen ions are turned into molecules of the element hydrogen. In our example, sodium is more reactive than hydrogen, so the sodium ions remain in the solution and the hydrogen ions are reduced to form hydrogen gas, which appears at the cathode as bubbles. There is a similar reactivity series for the negative ions at the anode. If the negative ion is less reactive than the hydroxide ions, which would be the case for chloride, bromide or iodide ions, then the hydroxide ions stay in the solution and the other negative ion is oxidized to form an element. If the negative ion is more reactive than hydroxide ions, then they stay in the solution and the hydroxide ions are turned into the element oxygen and water molecules. In our example, chloride is less reactive than the hydroxide ions, so the hydroxide ions stay in the solution and the chloride ions are oxidized to form chlorine gas, which appears at the anode as bubbles. We can work through some examples to make sure of how these rules apply. Here is a lithium chloride solution. Firstly, we can work out what ions it will contain. Li+ and Cl- from the lithium chloride, and H+ and OH- from the water. The Li+ and H+ ions will both get attracted to the negative electrode, and because lithium is more reactive than hydrogen, the Li+ ions will stay in the solution. The H+ ions will gain electrons and become hydrogen atoms, which will then pair up to form molecules of the element hydrogen, as shown in the half equation. The Cl- and OH- ions will both get attracted to the positive electrode. Because chloride ions are present, according to our rule, they will lose electrons and form molecules of the element chlorine, while the hydroxide ions stay in the solution. Now our electrolyte is a copper-2 sulfate solution. Again, we work out what ions it will contain. Cu2+ and SO42- from the copper sulfate, and H+ and OH- from the water. The Cu2+ and H+ ions will both get attracted to the negative electrode, and because copper is less reactive than hydrogen, the H+ ions will stay in the solution. The Cu2+ ions will gain electrons and become copper atoms, which will be deposited as copper metal on the surface of the cathode. The SO42- and OH- ions will both get attracted to the positive electrode. According to our rule, the sulfate ions will stay in the solution, and the hydroxide ions will lose electrons to form bubbles of the element oxygen and water molecules, which we can show using this half equation. One of the largest industries that uses electrolysis is called the chlor-alkali industry. The raw material is brine, which is a concentrated solution of sodium chloride from seawater, so it contains Na+ and H+ ions and Cl- and OH- ions. We saw before that electrolysis of sodium chloride solution produces hydrogen gas at the cathode and chlorine gas at the anode. The sodium and the hydroxide ions stay in the solution, so during electrolysis the sodium chloride solution turns into a sodium hydroxide solution. Here's the overall equation for what's happening. Sodium chloride plus water is turning into hydrogen, chlorine and sodium hydroxide. All three of these products are widely used. Hydrogen is used as a fuel and in the hardening of vegetable oils. Chlorine is used for killing microorganisms in water and for making bleach. and sodium hydroxide is used in soap and paper manufacturing. Just because the raw materials are abundant does not mean that these products are free or sustainable. There is a lot of expensive electrical energy required to do the electrolysis on a large scale. Generating this electrical energy uses up finite fossil fuel reserves and releases carbon dioxide into the atmosphere when these fuels are burnt. In industry, a diaphragm cell or membrane cell is used to do the electrolysis. It is designed with a separator which keeps the three products separate. A mixture of chlorine and hydrogen gas would be potentially explosive, so these two products have to be kept apart. In addition, the chlorine can react with the sodium hydroxide solution if we don't keep them apart. This is actually the basis for making bleach.